Thank you. I'm delighted. Everybody, please sit down and get ready for the talk. I'm delighted to introduce our next speaker, Sofia Garzón Mora, who will speak about fine polyhedral adjunction theory.
Yeah. Thank you for having me here. Yes, I'm going to tell you about this ongoing work I have with my advisor, Christian Hase, and maybe mention that some pictures are taken from work by Andreas Pfaffenholz. So how this talk will go is basically I'll introduce adjunction theory. I'm not sure anyone is very familiar with it, but I'll add then one more word and go to polyhedral adjunction theory. And the second part of the talk will be fine polyhedral adjunction theory, so basically adding more words. And here I'll tell you about two main results. So let's go to adjunction theory, and as a sort of introduction, so it came originally from toric geometry, where people study pairs of x, L, where x is a normal projective algebraic variety and L is an ample line bundle. But I'm just throwing words here. I'm not going to focus on the toric geometry side of this. So it was already studied in 1985 by Miles Reed and some other authors, and basically as a precursor of the minimal model program, so they aimed at the classification of varieties. But also, a little bit more recently, it's been used to classify toric varieties via duality as well in 2014. So let's move on to polyhedral adjunction theory. And what this is basically people have taken this dictionary between toric geometry and polytopes, and to translate all of these concepts from toric geometry into the polytope side. So basically what we study is lattice polytopes, which are basically polytopes that have integer vertices with integer coordinates. And then Dirocco, Hase, Neal, and Pfaffenholz, they published this paper with the same name in 2014. And maybe as a motivation for what follows, there is a fine version that was used to construct minimal models. Actually, this paper it appeared in 2020, but it just was published this month. So very hot topic of research, which was a very lucky coincidence. So I'm going to start very, very slowly. A polytope is just a set of points that satisfy some linear inequalities. And here I'm assuming that each inequality is defining a facet of the polytope. This will be important for later. And the main objects of study are adjoint polytopes. So basically, I'm taking all the facets and moving them in by some parameter s. That's at least 0. And so this is what polyhedral adjunction theory is all about. We study these adjoint polytopes. So let's take a look at an example. So let's say I give you this polytope, and I tell you to compute its adjoint polytope for some s. That's at least 0. And you say, OK, well, the easy case, just take s equals 0, right? And we get the same thing. But what if we take some s that's, for example, 3/2? Well, you see that you get a smaller polytope inside, right? And then this top edge becomes smaller and smaller until if you push further, it disappears. And then you can keep on pushing further. And if you see this top edge now appears, that's perpendicular to the original one. But that's completely OK. We can keep on pushing, and finally, we get a lower dimensional polytope. And if we push further, this will be an empty polytope. Yeah. So we can define some invariants on these adjoint polytopes. So for example, the Q colligree is, for historical reasons, the reciprocal of a quantity. And this quantity is the maximum amount you can push before it's empty. So the core will be this lower dimensional polytope that you have barely before it's empty. And for example, in the previous one, it was this one-dimensional segment. But maybe let this be this first talk where I ask you a question, so I hope you were paying attention. What was the Q colligree in our example? Can anyone tell me? Awkward silence, OK. Just almost. So it's 1/3 because of this reciprocal. Yes. Yeah, people always forget that. And the core is just basically, as I mentioned, this one-dimensional line segment. OK. So we can define a second invariant, and this comes from Earhart theory. So this is called the codegree. And this is the minimum integer, such that if I dilate this polytope by this integer, then I already get an interior lattice point. Right? And then if you take a lattice polytope, and if you think about the lattice points on its interior, then this will be the same lattice points on the adjoint polytope for s equals 1. Right? You can visually see it and imagine it, maybe. And so this gives us a bound. So the Q codegree is bounded from above by the codegree, which is bounded from above by n plus 1, where n is the dimension of the polytope. And so why will I talk about Cayley polytopes? Well, this is where we will use this invariance. And Cayley polytopes are interesting from the polytope view and from the toric geometry point of view. And from the polytopes, if I tell you something has a Cayley decomposition, this is already a very strong structural statement. And this limits our polytope. And Cayley polytopes are also important because they have projections onto unimodular simplices. And from the toric geometry point of view, people have studied them because their corresponding polarized toric variety is pre-rationally fibered, and they have interesting embeddings. So people from different areas have come to the same concept. And so this came into our work because we have this question. So we already know, and I've shown you, that the dimension of a polytope gives a bound for this Q codegree, right? So can we ask the reverse question? So if I have the Q codegree, can I derive a bound for the dimension of the polytope? And it turns out that we will be able to answer this question for Cayley polytopes, which is why I'm talking about them now. And so what is a Cayley polytope? Let me find the lattice width very quickly. So if you take a linear functional, and if you evaluate it at your polytope, you take the maximum and the minimum, and you subtract them. And if you do this for all linear forms, then you get, and you take the minimum, then you get the lattice width. And a Cayley polytope is just a lattice polytope of lattice width 1. So let me define now what a Cayley sum is. And this will be a Cayley polytope. And what I do is I take t plus 1 polytopes in R to the k, and I locate them on the zeros vector and on the standard basis vectors of RT. So basically, this is maybe better with a picture. So for example, I take P0, P1, P2, and I locate them on the zeros vector, on E1, and on E2, and then I take its convex hull. So this is what a Cayley sum is. And when we say something has a Cayley decomposition, it's because it can be decomposed in this way. And so there's this decomposition theorem that precisely tells me when something has a Cayley structure. And so if I take this parameter d, and I define it in terms of the Q codegree, then if I take an n-dimensional lattice polytope that has dimension at least this parameter d, then this will be a Cayley sum of lattice polytopes. And this even tells me in which R to the m. So this is already a very interesting theorem and very strong statement. And where can we also use this invariance? Well, it turns out that we can characterize the values that the Q codegree can take. So this is basically called the Q codegree spectrum. And in this case, we require two conditions. So the first condition is that I bound it from below by some epsilon. And the second condition is that the normal fan is alpha canonical. And what does this mean? Well, if I take any lattice point on its normal fan, and if I write it as a linear combination of the generators of the cone it belongs to, and then I require that the sum of these coefficients is at least alpha. And this is the alpha from the alpha canonical. Yeah, so I require these two conditions to characterize the Q codegree spectrum. And so there was this theorem by Pfaffenholz. And if you take a look at all the n-dimensional lattice polytopes such that these two conditions hold. So for example, the Q codegree is bounded from below and the alpha, they have alpha canonical normal fan, then the set of values it can take is finite. So we have already a lot of results where these invariants have been used. At least two, because I said I was going to talk about two in particular. So let's move on to fine polyhedral adjunction theory. So what this is, well, maybe I should mention first that this is not called fine because of the adjective, but rather because of Jonathan Fine, who presented this in his doctoral thesis in 1983. And what he proposes is to actually, instead of pushing by the facets, and if you remember at the beginning, I was very emphatic in making all the inequalities define facets, I want now to push with respect to all valid inequalities. So for example, if we take a look at this polytope, all these red lines are valid inequalities, even though they do not necessarily define facets. And so you might think this is a very complicated idea because now I'm dealing with infinite number of valid inequalities, but this actually paves the way into a very nice theory. And so we can redefine all this, and basically we can take now fine adjoint polytopes. So in this case, I'm not pushing by all valid inequalities, but I am pushing by all valid inequalities, but not only the facets. And then we can also redefine the this invariance I told you about. So the fine Q colligree is I now take this reciprocal of this quantity that you can push by all valid inequalities and before it's empty. And also, well, the fine core, you can let your imagination run wild and figure out what it is. And so let's take a look at how this differ. So in this side, I'm going to take original adjoints of a polytope, and on that side, I'm going to take fine adjoints. And so you already see that if we push in by a little bit, then on the fine adjoint side, we're going to get this 2 extra facets, right? Because now I'm introducing these valid inequalities that correspond to this parallel lines that are pushing inwards from the sides. Okay, a lot of nodding, that's great. Okay, so we can keep pushing, right? And on the side of the fine adjoints, then we already get a square. So we basically lost all the structure of the original polytope. And while here, I keep on getting smaller and smaller hexagons. So let's keep pushing and until we get this core. And the core on the fine case is just a point, while the core here is a one-dimensional line segment. So they don't even have to be contained in one another. They don't even have to have the same dimension. I can have also the inverse case examples where polytopes have fine cores that are one-dimensional, but original cores that are just 1 point. Right, so then we can restate our main results where we use this invariance. And so we can talk about the fine decomposition theorem. So basically what I'm doing is redefining this parameter d for the dimension, if you remember it for the Cayley polytopes. And I'm redefining it by just replacing this Q colligree with the fine Q colligree. So it turns out that the Q colligree is bounded from above by the fine Q colligree. So can you see where I'm going with this? So what does it tell me if I'm subtracting something bigger now? And this is where you shout, we get something smaller. Yeah, and so basically we restated this theorem and we now changed this bound in terms of this fine d, which means that I now have a lower bound than before for the dimension of a polytope to be a Cayley polytope. So we can restate one result, and we get the same result with basically the same proof. So it's already very nice. And then we can talk, this theorem is slightly stronger because we're subtracting something bigger, that's it. And we talk about the fine Q colligree spectrum as well. So we wanted to basically check whether this condition also holds of the finiteness in our case. And it turns out that it's even nicer than you might imagine because we require only one condition. So before we had this horrible condition on the normal fan, which was alpha canonicity, which I hope some of you got from the definition. If not, that's okay because we can forget about it now. And so we just require that the fine Q colligree is bounded from below by some epsilon, and we can drop the alpha canonicity assumption just because pushing by all valid inequalities restricts very heavily the values that the fine Q colligree can take. And so we get the same theorem as before. And so we restated it, and we just look at the set of n-dimensional lattice polytopes that have fine Q colibri bounded from below. And it turns out that the spectrum is also finite in this case. The proof is even nicer, shorter. So it's a good thing that we're now looking at an infinite number of valid inequalities, which is kind of counterintuitive. Yeah, so maybe what we've done is we started with original invariants and adjoints. Then we redefine them by adding the fine word to them, right? And then, so we started with some invariants that play a role in the Cayley structure of polytopes under Q colibris. And maybe I can mention also here that projections didn't work very nicely before, but I can also expand about that on the question, so maybe a little hint. And so we obtained stronger results and easier proofs about Cayley polytopes, Cayley decompositions, also projections, and fine Q colibri values. So maybe let me just mention what my advisor likes to say. He just says, the fine theory is nicer than the old theory. So we should all look at it. Yeah, this is a little fast than I expected. So the bounds, we have some open questions. And so this has been studied by a lot of people. So Dickenstein and Neal, De Rocojas and Neal and Paffenholz, and many more. And they studied bounds for Cayley polytopes. And so Cayley structure, decompositions, and this kind of thing, also from the toric geometry side. So this is not only from the polytope side. And so can we get even better bounds? So we just got a better one, but are there even better ones? And can we play the inverse game? So can we translate all this fine invariance into toric geometry? Because before I told you that we started first from toric geometry and then moved on to polytopes, but can we go back? And maybe what are other results from polyhedral adjunction theory that can still hold in the case of the fine adjunction theory? And also there's lots and lots of open questions. And so I'm happy if you have any more open questions, so just come to me. Thanks for listening.
Are there questions? Yeah. Alejandro.
For
like, say, I think there are sums, or certain of them, do you get some very bounds type in that case?
Can you repeat the question?
Yeah. Are the bounds tight for generalized permutohedra in the case of Cayley decompositions? So I haven't looked at them. That's a very good question. But I think they might not be that far off. And I'm also pretty sure that in lower dimensions, that this bound that you get from the fine case and the normal case, it's pretty close. So that might also be tight in that case. But maybe higher dimensions, it differs a little bit. Yeah.
Do you? Yeah.
So I just wanted to know, so when you were doing the fine case, you said there were infinitely many inequalities?
Yeah.
But then, I guess if that's the case, then how can you compute them? Or is
Yeah, so the question is, in the fine case, I told you many times that we have an infinite number of inequalities, so can we compute them? And this is yes, this is very nice. Maybe I can even draw a picture. Yeah, so it's basically you take a polytope, and let's just take this very easy one, and then you take a look at its normal fan. So I'm using inner normals, but that's okay. And you take a look at all the primitive generators of the rays of the normal fans, and then you take its convex hull. And basically, the points, the lattice points that you get in this polytope, they will correspond to valid inequalities you want to look at. So this is a very nice characterization, and then from this you get that this is a finite number that you are interested in, and also that the adjoint polytopes are polytopes as well.
Any other questions? Yeah.
Is there a relation between the Ehrhart polynomials of the core and the
is there a relation between the hard polynomials of the core and its original adjoint? So yeah, there is one because you can think of them as projections. So of course they will hold, but in the fine case, it's even monotone. So this will imply a relation of monotonicity as well in the, for example, H star polynomials, but not necessarily in the other case. There are horrible polytopes. Yeah.
More questions, anyone? Oh, yeah.
Well, that was my first question. Thank you, Aaron, for stating the question. But my second question is like, do you know, in the original case, it seems that depending on how you choose S, I think one is you can have dilates of one polytope, right?
Yeah.
And then until it becomes empty.
Uh-huh.
Do you know how fast we're losing those lattice points? Or I mean, I feel like it's more difficult in the fine case because it changes shape.
Yeah, that's a great question, thank you. So the question was, so if we keep pushing on this adjoint polytopes, and at some point I'm going to lose an edge, and so is there a way to measure how fast this happens? This is a, yeah?
That way, and also counting the lattice points.
And also counting the lattice points. Yeah, so the first question, let me just answer that. So you've unlocked one secret slide. Yeah, so this is actually another invariant that's called the NEF value. And the NEF value tells you exactly when that is. So you take a look at the reciprocal of this maximum distance you can push before the normal fan is different. Right, and this is an invariant. This comes from actually toric geometry. So yeah, I have a very nice picture as well. And so yeah, let me just go back. So in toric geometry, the NEF value is, you look at something very, let's say, algebraic, and then you can think of it as like moving outwards in this ample and NEF cones. But in polytopes, this is an invariant as well, and you can classify more things with this invariant. So that's basically, yeah, the short answer.
Any other questions? Actually, I have an announcement, which is if you're having a headache, it might mean that you had too much fun in Napa Valley, but it also might mean that you are dehydrated, and the coffee break would be an excellent time to have lots of water and make your headache go away. So I've encountered one or two people with this already, so that's why I thought I would just remind people not to get dehydrated. Today's supposed to be very hot. Any other, that gave people more time to think of more questions. Is any more, or are we all set? Okay, well, let's thank the speaker again.